Now let's find out our capacitance for a spherical capacitor. We will use the same figure uh, as a central cross section of a capacitor that consists of two concentric spherical shells of radii A and B, and a Gaussian surface is also a sphere of radius r, concentric with the two shells. Now the value of the charge would be, in which 4 pi r square is the area of the spherical Gaussian surface. So this will become E is equal to 4 pi epsilon naught q over r square. This equation we already solved we already solved this is the expression for the electric field due to a uniform spherical charge distribution. Now if we substitute the expression into this equation, this one we would be able to find out the potential. So V is equal to, we are following the general strategy that first we assume a charge and then we find out electric field, then move towards the potential, and at the end we calculated the capacitance of a specific configuration. We substituted the displacement as minus dr. It means the direction is inward, radial direction is inward. Then now let's simplify it by using the limits. We will get the expression in this form: 1 over a minus 1 over b. Now let's move towards the capacitance, which would be equal to I have simplified this stuff here. Now this is capacitance of a spherical capacitor, and again the point to be noted is it depends on the geometrical configuration, on the radii of the shells of the spheres. Now we can also find out the capacitance for an isolated sphere. What we will do in this one, we will modify the same equation to find out a capacitance for isolated sphere. We assign a capacitance to a single isolated sphere conductor of radius r by assuming that the missing plate is a conducting sphere of infinite radius. After all, the field lines that leave the surface of a positive charge must end somewhere. For example, this one is a positive charge sphere and it is isolated. So the field lines will end somewhere, and we suppose that that is where it ends, that is at the infinite distance or at some infinite radius. So to find the capacitance, we first write this equation as A over 1 minus A over B, and then let's B reaches to infinity and we substitute R for A, then this equation becomes 4 pi epsilon naught into R. So this one is the capacitance for a single isolated sphere when the other sphere which surrounds the positive charge is at a infinite radius, or it is at infinite distance. So in today's lecture we understand the concept of capacitor, how we charge the capacitor, and we also find out the capacitance for different configurations: parallel plate, cylindrical, spherical, and for an isolated sphere. So in case you have any difficulty, you can discuss with me during the discussion session.